Welcome to Lesson 13C, Slinn Model, Diffusion Effects. We're going to discuss something kind of interesting today about diffusion and Brownian motion. Here's the problem. The Calvert in England model breaks down for very small particles. Why? Well, if we consider our raindrop and some air streamlines, like we've been talking about, and relative to the drop, the air is moving up at VTC. For very, very small particles, they pretty much move with the streamlines, and so they don't impact the particle. In other words, there's negligible inertial separation or impaction of the particles into the drop. Another way to think about it is that R1 goes to zero as dP goes to zero. The particles just follow the streamlines. So the C&E model basically predicts very close to zero single drop collection efficiency. But for very small particles, Brownian diffusion becomes significant. You probably remember Brownian diffusion from your physics class. Air just kind of vibrates at very tiny distances, and there's a lot of randomness going on due to the molecules banging against each other. So what really happens is these air streamlines are wiggling all around instead of going nice and straight, but they have a lot of randomness to them. And so very, very tiny particles will follow those air streamlines pretty much, and some of them will end up getting collected due to Brownian motion, not any kind of inertial separation. They're pretty much following the air streamlines as they vibrate, and then they hit the particle. When we say very small particles, we're talking about particles that are less than typically about 0.1 microns. So Brownian diffusion or Brownian motion becomes very important when you have really, really small particles. Let me explain this graphically. Let's plot single drop collection efficiency versus particle diameter as we typically do. This is the grade efficiency for a single drop. So we'll go from 0 to 100%. And I'm going to put just one diameter here. This will be my 0.1 microns. The C&E model looks something like this. It's your typical S-curve, and it always falls off when the particles get big. You really can't trust it for too big a particle. But my point is, for very small particles, it's pretty much zero. This is the Calvert in England model. But what actually happens, and I'll use a different color, is that around 0.1 microns or so, you start to get something that causes A to dP to go up, and that is the Brownian motion. This is the actual A to D with Brownian motion taken into account. The C&E does a pretty good job for larger particles, but it does a terrible job for very small particles. But when you add them both together, you can actually get the correct result. What we're saying is that there's some range here, and it's around 0.1 microns or so. It depends on the droplet size and density and all that stuff, but typically around 0.1 microns. Anything below that, Brownian diffusion dominates. And there's another range here above some diameter, inertial impaction dominates. The interesting thing is that there's this region in here where neither inertial impaction nor Brownian diffusion work. Therefore, A to D dP is very small in this region. So in this zone here, raindrop does not collect particles very well at all. They're too big for Brownian motion to work, and they're too small for inertial impaction to work. So they're in this kind of never land where nothing works for them. You can't effectively collect those kind of particles in that range, in this range here, with raindrops. There are many models out there for Brownian diffusion effects on single drop collection efficiency. So we picked one for the big particles. That was the Calvert in England. We're going to pick another one for Brownian motion or Brownian diffusion. This one's going to be the Slinn model, S-L-I-N-N, way back from 1983. What he did was model Brownian diffusion for very small particles being collected by a drop, which is exactly what we're talking about. This is perhaps the simplest model out there, and this is the only model we'll use in this course. What we're actually going to do is combine the CE and the Slinn model, so we'll use the Slinn model here. But since it goes to zero for large particles, and since CE goes to zero for small particles, you can just add the two up without harming anything. And that's exactly what we'll do. We'll just add those two up for our total removal efficiency. I typed up all the equations, and they're also on the equation sheet. So let me just quickly go through this. First, we calculate a Schmidt number given by this. We know everything here: mu, dP, particle diameter, rho of the air. There's no subscript. Kb is the Boltzmann constant you may remember from physics class, given here. Temperature and Cunningham. That Cunningham is for the particle, not the collector. So make sure you don't mess that up. Reynolds number is based on the collector, though. So rho dC VTC mu. And then here's Slinn's model for single drop collection efficiency that is accounting only for diffusion, has nothing to do with inertial impaction. Finally, we can just combine, and that's what I just said above. We can just add the two, Calvert and England plus Slinn, together to get our total. So the total single drop collection efficiency is given by this equation, where we're just adding the two together, where this KP is part of the C&E model. So this is from the C&E, this portion, and then this is the new part that we're adding, the Slinn model. From now on, we'll use this combined equation for all calculations of A to D grade efficiency. It includes both the Calvert and England and the Slinn models. So again, Calvert and England is for larger particles, and the Slinn is for very small particles. Calvert and England is based on inertial separation, and Slinn is based on Brownian diffusion. And we're just adding those two together. Let's do an example problem. We have raindrops that are 50 microns in diameter, water, so it's unit density. They're falling through dusty air at a given temperature and pressure. Small aerosol particles with another density that's a little bit different than the collector, and diameter is 10 nanometers. This is very, very tiny. They're suspended in the air and are collected by the raindrops. We need to calculate a single drop collection grade efficiency, A to D, as a function of dP as a percentage to 3 significant digits. And we're going to include, as I said, both the C&E and the Slinn models. So how do we solve this? Well, first thing I did was use my software to calculate VTC for the raindrops. Got this value. VTP for the particles, 10 nanometers. Watch your units, that's nanometers. I got this very, very tiny velocity. The Cunningham correction factor for these tiny particles is actually pretty high, 24.29. And here's just a summary of the equations I just showed you. So it's just a matter of plugging in the numbers. At the given temperature and pressure, I use my Sutherland law, ideal gas law, and our equation for lambda to get those properties. Make sure you can duplicate all of this with software. Don't do this by hand. I'm going to do it by hand here just to show you that all the units work out and all that. We get a density, we get a viscosity, and we get a lambda, mean free path. I used that to generate my Cunningham correction factor. I generated a different Cunningham correction factor for the collector drops. Next, I calculated Kp from the equation up here. I'll plug in the numbers. Remember, that C is for the particle. Difference between rho p and rho of the air. When you do the conversion, 10 nanometers is 1 times 10 to the minus 8th meters, and that's squared. And then the absolute value of the difference in speeds, the collector speed minus particle speed. You can see that this guy is negligible compared to this guy. But we include it, especially in the software, because we're going to extend this to a range of dP, and then that won't always be the case. And then divide by 9 mu dc. Watching all our units, of course, you can verify that they all cancel, as they must, because Kp is a non-dimensional parameter. We get Kp equal 2.160 times 10 to the minus 5. It's dimensionless, no units. Once we have Kp, we can calculate A to D dP for the Calvert and England model, and just plug that in and do it. I'm keeping only 4 digits here, but in my software, I had many more digits than that, of course. I get 9.5 times 10 to the minus 10th. In percentage, that's 9.5 times 10 to the minus 8th percent, which is very small. That shouldn't surprise us if you look at what I was talking about up here. We're talking about particles that are way down in this region. So the Calvert and England model for inertial impaction is giving you a very, very tiny number. We'll get a much bigger number from the Slinn model that we'll do next. So for the Slinn model, we need to calculate the Schmidt number first. We'll use this equation up here. 3 pi mu squared. This is probably the first time you've ever seen a viscosity squared term. I assure you it's right and the units work out. And then we have dP divided by rho, Kb, Boltzmann constant. T must be in K, not degrees C, of course, so we convert. And finally C, that's the C of the particle. A joule is a Newton meter. A Newton is a kilogram meter per second squared. Crossing out units, there's 2 kilograms on the denominator and 2 on the top. All the meters cancel. Okay, here's a good reason for always putting in your units. I happened to mistype that as the units of viscosity instead of density, and I was having some trouble. And now I've corrected that, so my seconds do indeed cancel out, and my meters also cancel out. I get 291.9 for the Schmidt number, also a non-dimensional parameter. I get REC for the collector particle, the drops. That comes from my iteration for VTC, so I got that from my software. REC turns out to be 0.2158 for these collector particles. I should mention here that we can use Stokes approximation for the particle terminal settling speed. That Reynolds number is really tiny. But for VTC, we can see that our Reynolds number is not less than 0.1, although you won't have a whole lot of error if you'd use Stokes for this particular example. I would encourage you to always do the iteration, however, because again, we're going to be extending this to a range of dP and Stokes will not always work. So just program it up once and you're done. I always iterate even when I know it's in the Stokes range. Then we calculate A to D using Slinn. That's from this part of the equation, and you just plug in the Reynolds number, the Schmidt number, etc. There's no units in any of these numbers, and I get 0.08793. So A to D for Slinn ends up being 8.793%. Then we simply add up the value for CE and the value for Slinn. You can see that the CE value for this particular case is negligible, and even to many more digits than this, I get the same answer as my Slinn. So rounding everything off to 3 digits finally, my answer is 8.79%, about 8.8%. These really aren't 3 significant digit accurate equations, but we'll always give our answers to 3 digits anyway. So lastly, I used Excel to repeat this for a range of particles. I went all the way from 0.001 microns to 100 microns, and 50 is the diameter that we are doing as our test case. I really should have stopped this around 25 or so. So all this is bogus because these particles are bigger than the raindrop. I also did it for 100 and 200 micron raindrops. One comment that you'll see here is that the Slinn model also has some problems. For very, very small particles, the Slinn model can predict A to D greater than 100%. That's just how the equations turn out. So it's good to use if statements in Excel. If it's greater than 100, just set it to 100. What does that mean physically? How could you have 100%? Well, it turns out that the Brownian motion is just so huge for these particles that it's predicting that pretty much everything hits. But it's not physically realistic. Of course, you can't have a removal efficiency greater than 100%. So anything up here is kind of bogus also. For these actual numbers, you can clearly see that region that I had showed you before, this range where neither CE nor Slinn work. So you have this range where it's very hard to remove particles in this range. And that's a kind of a physical limitation of collecting particles with raindrops. Finally, since these are so small down here, we often plot this on a log-log scale instead. We're still plotting percent A to D, but we put it on a log scale. You can see this region where it's very hard to collect these particles. They actually do have some A to D. It's just very hard to see on this plot on a linear scale, but on a log scale, it emphasizes that. It also has some other interesting features, like these 3 guys tend to be parallel to each other for very small particles. And again, larger raindrops do better in the CE portion, but it's the opposite case for the Brownian motion portion. The Slinn model's predicting that the smaller drop diameters here, 50, do a better job than the bigger raindrops. So if you're trying to collect really tiny particles, you'll want to use small raindrops.
But dude, you can't control the size of the raindrops, man.
That's true, Joe. But the next lesson, we'll talk about spray towers, which is kind of artificial rain that people use in a big tower to collect particles from an airstream using artificial rain.
Far out, dude. I can't wait to watch the next lesson.
So that's the preview of coming attractions.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.